The PageRank algorithm. Most of us have heard of the PageRank algorithm, which is very popular and was instrumental in building the Google search engine by Sergey Brin and Larry Page in 1998. This was their original paper right here. So the PageRank algorithm tells us how to rank or compute the relevance of a particular page when one is going and surfing the World Wide Web or a connected set of documents. So let's look at it a little bit in detail. So the PageRank algorithm is based on the random surfer model, which means let's say I'm a random surfer and I start on one of these nodes. Let's say I start from node E here. As a random surfer, I would pick each of these nodes is connected to some other nodes. So there are some outlinks from each of these documents to other documents. So I will pick one of these outlinks at random and follow it. So from E, let's say I follow this outlink and go to F. Now I would pick another outlink of F at random and follow it. Let's say I go to B. And now I pick an outlink of B and I might end up at C. And if I pick an outlink of C, I might again end up at B. And I keep doing it for a very long time. The PageRank tells us what is the probability that I end up on a particular document. So the probability that I end up at a particular document after a lot of these iterations is an indication of the relevance or the rank of the document. Let's see how this works in a little bit more detail now. So let's take a very simple graph of just 4 documents, A, B, C, and D. All the 3 other documents link into A, while B has only one in-link, C has 2 in-links, while D has no in-links. The PageRank computation is as follows, mathematically very simple. The PageRank of a particular node is summation over all the other nodes that link into it, all the other nodes V that link into it, PageRank of V divided by number of outlinks of V. So I'm just aggregating the PageRank of all the nodes that link into me, but I'm normalizing it by the number of outlinks of that node itself, because it's only contributing a percentage of its relevance to me because it has multiple links going out. Right? So if we just look at the computation here, PageRank of A is nothing but PageRank of B divided by outlinks of B plus PageRank of C divided by number of outlinks of C plus PageRank of D divided by number of outlinks of D. And this is because all the other documents are linking into A. Now, if I take the document B, there is only one in-link. So PageRank of B is nothing but PageRank of D, which links into it, divided by number of outlinks of D. Similarly for C and D. And we see that for D, since there are no in-links at all, there are no terms that I can write here. So this is based on the random surfer model. A variation of this that has been used in the original paper is the random surfer with restart model, where we have a damping factor which says that a random surfer can follow one of the outlinks at random, but with a small probability they can also pick another page in the graph. So this means that the PageRank of A will have a damping factor, a small damping factor 1 minus D plus D into whatever we had earlier. PageRank of all the pages that are linking into it divided by the number of outlinks of that page. So bottom line, this tells us that every page has a small probability of getting hit, irrespective of what links it has, and also depending on the damping factor. And also a page that has more in-links has a higher probability of, bubbling up or being shown. And a page that has a low PageRank or a page that has fewer in-links has a low probability of being arrived at. So we can put the same thing in the form of a matrix and think of it as a Markov chain problem, if you have heard of that before. Otherwise, please don't bother about that. But we can put this in the matrix form as follows. So we can say that, let's say R is the set of page ranks, is a column vector of page ranks. Then we can write the basic equation, the random surfer model, as R equals this matrix here into R, where the matrix itself has L of Pi to Pj is the number of outbound links from page J to page I. So if we simplify this, we will just end up with this equation that we have seen here. It's just a way of saying this. But and then we can modify this to add the damping factor as well. And the nice thing about this is that when we actually think of this as a Markov chain, and think of it as think of R as the stationary distribution. If we solve for the stationary distribution of the Markov chain, it's nothing but a set of page ranks. And what it tells us once again is that it is a way to explain this intuitive notion that the page rank is nothing but where we land up after we take a lot of iterations of this formula that we see here. So when we keep doing this again and again and again and again and again, what is the probability that one lands on a particular node? That is basically the stationary distribution, or the page rank. So there are many variations of the page rank. In fact, most of the practical cases where page rank is used right now is one variation or the other. We'll look at two variations here. One is the personalized page rank, which is instead of saying what is the popularity or what is the relevance or rank of a document overall, we want to say what is the relevance or rank of a particular document with respect to a initial set of seed nodes that we care about. Right? We will see an example of this. And this is just a variation of the previous model mathematically, but we won't go into the details. And there is an undirected page rank. That's another variation where we can just look at so basically this is a graph of undirected links instead of directed links. But we can handle this use case by just saying that each undirected link is a pair of directed links. So if I have an undirected link from A to B, it means there's a link from A to B and B to A. So I can just treat it like that and use the same page rank algorithm. So let's look at a couple of applications of page rank algorithm. Other than the popular web ranking, let's look at a few other applications to get some more perspective here. So ranking tweets. So one could look at the Twitter graph as follows. Suppose I have a bunch of users, Grace, Samantha, John, and so on. And if a user follows another user, I have a link from that user to the other user. If a user tweets something, I have a link from the user to the tweet. And if a user retweets something, I have a link from the user to the tweet again. So this is my set of connected nodes. And now I can use the PageRank algorithm to find the relative ranking of all these tweets. I can find the page rank of every node. And if I take the page rank of these tweets, it will give me a relative ranking of the tweets. Which tweets are more relevant or globally important. Now, if I use personalized page rank, I can find out from Samantha's perspective, which tweets are more important. Or from the perspective of John, which tweets are more important. I can use the personalized page rank for that. And just to get some perspective, the personalized page rank is just the random surfer model with restart, where the restart involves going back to that original page instead of going back to some random page. And we won't go into the details of it though here. And then another example is the product recommendation use case. So here again, let's say we have a set of users, Grace, Samantha, John, Carter, and here we have a bunch of books, or these could be movies or products or songs, but here these are like names of books perhaps. We have like Harry Potter, Lord of the Rings, Hobbit, Percy Jackson, the Foundation series, Dune, and so on. Now we can use, so this is a undirected graph, and using the variation for the undirected graph, we can compute the page rank for each of these nodes here, very similar to what we have talked about earlier. And we can get the relative ranking of all these books. So if a random user goes, what are the most relevant books that it makes sense to, show? We can also do personalized page rank to say from Samantha's perspective, what are the most important books? What are the most important books to show to Samantha? What are the most important relevant books to show to Carter? So this is an example of product recommendation. Note that the PageRank algorithm that we talked about is extremely simple to code up, the basic version of it, and even the variations are not too hard really. So we've just seen the PageRank algorithm. We've seen how the PageRank algorithm can be implemented. It's pretty simple, just a few lines of code. And we have seen a few variations of it and a couple of applications. Thank you very much.